Before we continue our discussion to TV and PV diagrams, let's review 3 important points on our PT diagram. Point 1 is our triple point, where all our phases can exist simultaneously. Point 2 is our boiling point, where water vaporizes at standard temperature and standard pressure. Point 3 is our critical point, where if we go past, there is no phase boundary at this point, and we become a supercritical fluid. We'll discuss this more later. A TV diagram shows the relationship between temperature and specific volume for lines of constant pressure. And a TV diagram for water is shown below, where we have temperature on our y-axis and our specific volume on our x-axis. The blue line represents a saturated liquid curve. The red line represents a saturated vapor curve. Everything constrained by these lines is referred to as the vapor dome. Now let us look at the particulars of a TV diagram. Say we have fluid at 100 degrees centigrade. Our saturation pressure is 101.325 kPa. That is to say, 100 degrees centigrade is our saturation temperature corresponding to a pressure of 101.325 kPa. The substance is referred to as saturated, as denoted by the gray region within our vapor dome, if our substance exists at saturation temperature and saturation pressure. Note in our previous example, where we are heating water within a piston cylinder device. Once we reached 100 degrees centigrade at a pressure of 101.325 kPa, we proceeded to change phase. That is, we went from our saturated liquid curve to our saturated vapor curve. And to do such, we had to add energy, i.e. the latent heat of vaporization. So the line going from our saturated liquid to our saturated vapor curve represents the amount of energy we have to put in to change our phase from a liquid to vapor state. It also shows us how much our specific volume changes. Now note on our TV diagram that we have a line of constant pressure that extends from the bottom left and rises to the top right until we intersect our saturated liquid curve. Then we move across our vapor dome in a horizontal fashion, both in a constant temperature and constant pressure process until we reach our saturated vapor curve. Then we move outside our vapor dome up and to the right, following a line of constant pressure. Now note in this illustration that the lines outside the vapor dome are representative and do not reflect actual numeric values between the relation of pressure, temperature, and specific volume. This is an illustrative diagram for everything outside our vapor dome. Now, there are very important classifications based upon our relationship to Tsat and Psat. For instance, if our temperature is less than our saturation temperature for a given saturation pressure, this is referred to as a subcooled liquid, and this region is indicated by the green shaded area on our TV diagram. For instance, if our saturation pressure is 101.325 kPa, but our temperature is 50 degrees centigrade, we are existing within our subcooled liquid region. Now, if our pressure is greater than our saturation pressure for a given saturation temperature, this is referred to as a compressed liquid, as denoted by the shaded blue region. Say, for instance, our temperature was 100 degrees centigrade, but our pressure was 200 kPa. We would exist within our compressed liquid region. If a substance exists as 100% liquid at a saturation temperature and corresponding saturation pressure, this is referred to as a saturated liquid, as denoted by the blue line on our TV diagram. Note our saturated liquid curve has unique specific volumes associated with a unique temperature value. If a substance exists as 100% vapor at a saturation temperature and corresponding saturation pressure, we call this a saturated vapor, and this is denoted by the red curve. Note there is a unique specific volume for temperature entry. Lastly, if a substance exists as a vapor at a temperature greater than our saturation for our given saturation pressure, this is referred to as a superheated vapor, and this would lie in the shaded red region. For instance, if we have a saturation pressure of 101.325 kPa, but our temperature is 200 degrees centigrade, we would clearly exist within our superheated vapor region. Now, we can also visualize the relation between our pressure and specific volume on a PV diagram. Our PV diagram is very similar to a TV diagram, except we have lines of constant temperature starting from the top left, moving down toward our saturated liquid curve, then moving horizontally across our vapor dome, and then down and to the right through our superheated vapor region. For instance, if we had a pressure of 100 kPa, our corresponding saturation temperature is 99.6 degrees centigrade. We can take our TV, PV, and PT diagrams and construct a thermodynamic surface, which is seen on pages 45 and 46 of your text. Now, we will not work with this surface, for oftentimes this describes things happening such as sublimation and deposition, or melting and freezing. The focus of this class will be on phase transformations going from our liquid to our vapor state. Let's consider an example. Given a TV and PV diagram of water, where we have a temperature of 325 degrees centigrade and a corresponding saturation pressure of 12,040 kPa. And we want to determine the following classifications of the substance based upon given temperatures and pressures. Our first given is a temperature of 325 degrees centigrade and a pressure of 20,000 kilopascal. We recognize that 20,000 kilopascal is greater than our saturation pressure of 12,040 kilopascal. Thus, we are going to exist as a compressed liquid for our given temperature of 325 degrees centigrade. Next, we're given a temperature of 325 degrees centigrade and a pressure of 8,000 kPa. Since our pressure is less than our saturation pressure for our given temperature, we're going to be existing as a superheated vapor. Now, say we're given a pressure of 12,040 kPa and a temperature of 200 degrees centigrade. Since our temperature is less than our saturation temperature for our given pressure, we're going to exist as a subcooled liquid. And lastly, if we're given a temperature of 325 degrees centigrade and a pressure of 12,040 kPa, we're going to exist as a saturated substance. That is, we're going to exist on the line that extends between our saturated liquid and saturated vapor curve. Thus, we'll need one more unique identifying property to tell us where we exist, i.e., specific volume.